The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, so today we're going to start the last section. We're going to do 3 lectures on phase diagrams. And I've given this the label here of stability, sustaining the solid state. We've talked a lot about the solid state in 3091 as the vehicle for teaching the rudiments of chemistry. Now, one of the things we have not talked about is what are the conditions that sustain the solid state? How do I know whether something's going to be a solid or a liquid or a gas? And this is very important. For example, if you're in a foundry, you're running place that's making auto parts, you have to know what the solidification temperature is of the alloy so you can get the parts out quickly and keep productivity high. It's even important in failure analysis. You know, when they were looking at things like the rubble from the World Trade Center, by understanding phase stability, the thermal history was imprinted in the metal. It's possible to determine what temperatures were achieved and therefore what the chain of events was that led to the collapse of those buildings. Now you might say, well, isn't this straightforward? I mean, for example, you just look up the melting point, a boiling point, water, 0 degrees C, melting point, boiling point, 100 degrees C. Well, suppose you decide to realize your life's ambition, you're going to go and scale Mount Everest. So you paid $10,000, you get a license from the Nepalese government, and you're at base camp at 20,000 feet, and you're sitting there, you got your campfire going, you've got a hankering for a hard-boiled egg. And you put the eggs in the boiling water and you cook them 10 minutes and take them out and they're still runny. So you say, well, I must have lost track of time. So you cook them 20 minutes and they're still runny. And you cook them 30 minutes and they're still runny. And you eventually come to the realization that at 20,000 feet, the boiling point of water is below the denaturing temperature of egg yolk. So now the boiling point is a function of pressure. It's a function of pressure. So, you know, we could have one of these Iron Chef cook-offs, only the dish is souffle, only we'll have the contest at Flagstaff, Arizona, where the altitude is so high that the classical recipes won't work because the boiling point, the atmospheric pressure, and everything conspire so that you're not going to be able to support the souffle. So you're going to have to understand phase diagrams. In fact, if you understand phase diagrams, that's your ticket to being a 4-star chef in the kitchen. Well, here's another place we can look at where pressure has an important role. Let's look under the hood of a car. You're running an internal combustion engine. So this is the engine block, and there's combustion going on inside. We've got to keep this thing from overheating. It could damage the metal. In the extreme, you could melt the metal. So we've got cooling channels in here. We've got cooling channels with water flow. But then the water's going to heat up and the water's going to boil. So we've got over here the radiator. So it's really a double cooling system. The water cools the block and then the radiator cools the water. So how's that going to work? Well, here the temperature is on the order of about 90 degrees C, and here the temperature inside the engine block is much greater than 90 degrees C. It's several hundred degrees C inside that engine block, and we've got water going like this. So we've got cooling, water flow in this manner, and now cold water goes in and hot water comes out, and then we get into the radiator, and we've got channels here, and we've either got a fan or some kind of airflow. And so now what's the gambit here? I want to see what's going on inside this radiator. So if this is the wall of the radiator, and in here I've got water, and over here I've got air, the idea is to have a high heat flux to get the energy out of the water and cool it down. Now, if things get really, really hot in here, let's say you're zooming along down the highway at about at about 65 miles an hour, and all of a sudden you come upon a collision and you have to go to a dead stop. all that energy in the engine is now dumped, and the water could overheat. And in the extreme, if it overheats, it can actually go into a boil. And this is bad because heat transfer is really good between a liquid and a solid, and it's really poor between a gas and a solid. This is a low heat flux. Low heat flux. And this is bad. High heat flux, that's good. All right, this is the bubbles. This is boiling. And why? Because what transfers energy? It's the atoms. And what's the atom density in a liquid versus the atom density in a gas? You just have really crummy heat transfer. Really crummy heat transfer. That's why insulation involves dead airspace, because you have very poor atom density. So what can we do? What can we do in order to try to repress the bubble formation? Well, we said if we went up Mount Everest, we went to high altitude, the boiling point went down. So why did it go down? Because the atmospheric pressure is lower. So why don't we go the inverse here? And we'll put a pressure cap on the radiator and make the pressure go up. And when the pressure goes up, it exerts a back pressure and represses bubble formation. So by increasing pressure, we can increase the temperature and get the temperature up. So let's say P equals, if you look on the top of the pressure cap, it'll say 15 psi. And 15 psi is almost 14.7 psi, which is exactly 1 atmosphere, which in SI units is, and I know this to 6 significant figures, 101.325 pascals. Or, you know, from Torricelli, 760 millimeters of mercury. That's the column that's supported. So we're at 2 atmospheres pressure in there, and with 2 atmospheres pressure, we can raise the boiling point to 106 degrees C. And then what we can do is now change the composition. So we change the pressure, and I change the boiling point. I change the composition, add 50% ethylene glycol. Ethylene glycol, so now I got a 1-to-1 mix, ethylene glycol water, and that takes the boiling point up to 130 degrees C or 265 degrees Fahrenheit. So another example of how we can manage systems. So what I'm showing you by these several examples is that the boiling point is a function of pressure and composition. So we can tune the boiling point. See, we were tuning materials properties before, but now we're tuning physical chemical properties, because that's what chemistry is all about. It's about control. It's about management. Management to advantage. So how do we know what to do here? Can we predict this from first principles? No. Systems are still too complicated. Our models aren't robust enough. So instead, we turn to an archive. So we have phase diagrams. Phase diagrams. And the phase diagrams guide us in our search for better management of material systems. And these are stability maps. They tell us which phases are stable under which conditions of pressure, temperature, composition. They're stability maps. You can consider them as archives. They're archives. So that's what I want to talk about, because it's really important to know this stuff. Okay, so what are we going to do? So first of all, let's, I don't want to write on that one. This is interesting. This could be a work of art. I'd hate to desecrate it. You like? This is really good. So I'm just going to leave that. That's very good. That's excellent. Okay, so now, all right, so I've been talking about phase. What is a phase? Let's get the right definition here. What is a phase? It's a region of uniform chemical composition. Just to get it down, it's a region in a material. Region of uniform chemical composition. Uniform chemical composition. And it has these other properties. Uniform chemical composition. It's physically distinct. Physically distinct, and I'll show you by examples, but let's just get the definition down. It's physically distinct, and in the extreme case, so that means it's bounded. If it's physically distinct, that's a fancy way of saying that you can put a boundary around it. It's bounded. And then the other property that it has, it's mechanically separable in the extreme. Mechanically separable. Mechanically separable. And so that's in the case where you have a multi-phase system. You can point to the different piece. So what I'm going to do is I'm going to give you some examples. And so I'm going to let circle P equal number of phases. Number of phases. And I'll give you some examples. Why am I using circle P? Because just plain old P is already pressure. So pressure, so this is kind of Western motif, you know, like a circle bar ranch or something. So it's a P with a circle. That's my font. So that's how I say number of phases. So let's take a look at some examples. So here's some examples of P equals 1. So simple one is pure water. Pure H2O liquid. It has all of this. It's wherever I have the water, all right, here's some water. It's all of the same chemical composition. It is physically distinct. I can put a boundary around it. And in this case, there's nothing to separate because it's just a one-phase system. Okay, white gold. White gold is one phase because we have gold. Obviously, we have gold. If you market something as white gold that has no gold, you'll go to prison. And how do we make white gold go to its white color from the normal yellow? We add silver and we add nickel. And these are all FCC metals, and they substitute for one another on the lattice. And if you sample anywhere in the white gold, you get the same chemical composition and so on. Air is an example of a one-phase system. It's a gas, and in decreasing order, we have nitrogen, oxygen. So it's a solution. We're breathing a solution. Nitrogen, oxygen, argon are the main constituents. There's some CO2, some sulfur dioxide if you live near a power plant, NOx if you're near a tailpipe, and so on and so forth. All right? And then the last one I'll give as an example is calcio-zirconia. Calcio-zirconia, or cubic zirconia. Let's just call it cubic zirconia. The holidays are coming, so we better get cubic zirconia up here. That's the poor man's diamond. Cubic zirconia, which consists of a solid solution of calcium oxide in zirconium oxide. This is a solid solution, so it's continuous in chemical composition, identical. Now, contrast that with a two-phase system. So P equals 2 looks like this. So let's look at, instead of simple water, liquid, if I have ice cubes in water. Ice cubes in water. So now I have two different phases, and they're separated by state of matter. State of matter is the issue here. Because I have a solid, this is solid, and I'm going to put the boundary around them. The composition of the solid is different from the composition of liquid. They're both the same water, but you can tell it's a different crystal structure and so on, and I can put boundaries around it, and it's mechanically separable. You can pull the ice cubes out of the mix. Milk is two-phase. Milk, it has a fatty phase, and it has an aqueous phase. The aqueous phase contains the minerals. That's why you can drink skim milk and still get your calcium, because calcium, even the general public knows calcium is a mineral. It's not elemental calcium, it's a calcium compound, but it's ionic, it's soluble in water, and the fat contains the other parts, you know, from last day. This is one of the lipids, and so you have fat globules that are mechanically separable and distinct from aqueous. So they actually have a different chemical composition, different type of bonding. All right, this is largely nonpolar, and nonpolar doesn't like to dissolve in something that is polar and hydrogen bonded. So they phase separate. I've been saying phase separate all along, but now you know what we mean by phase separate. Here's a third one. This is really cool because you won't get this in any other chemistry class because only 3091 talks about such things. David, could we cut to the document camera? I want to show you a piece of snowflake obsidian. Snowflake obsidian. Obsidian is a volcanic glass. All right, so here's the piece of obsidian. And what you're looking at is the black area is the glassy part, and the white is actually some of the obsidian that has decided to devitrify, and it is turning crystalline. And so those are islands of obsidian crystal sitting in a matrix of obsidian glass. If we can go back to the Back to I picked that up in Yellowstone Park. It's fantastic. There's a wall, just a wall of obsidian that comes down. And I think I've got an image here. There it is. This one I pulled off the internet. So this is the crystalline phase, and this is the amorphous phase. And the overall composition, it's a glass, it's a silicate. And why isn't it transparent to visible light? Because it's got iron in it. The iron gives it the absorption capabilities. Its band gap is invisible, so it's black. But then when this crystallizes, it's got a different index, and it's mainly SiO2. It's really the cristobalite phase of the obsidian. So that's cool. So this is actually differentiated on the basis of amorphous and crystalline. Amorphous and crystalline of something that's virtually the same chemical composition. So this could give you an idea of what happens in the area of phase separation. Okay. Now, the second thing that I have to bring to your attention is that these phase diagrams treat systems at equilibrium. They're stability maps, and they treat systems at equilibrium. So what is equilibrium? Let's just get one time up here a definition of equilibrium. Equilibrium is a condition in which there is no net reaction. No net reaction taking place. The system could be reacting. If you're looking at the ice cubes in water, the ice could be dissolving and some of the water could be freezing, but overall, with time, there's no net reaction. It's a dynamic system with no net reaction. And it's characterized as the lowest energy state. It's the lowest energy state. Systems strive towards equilibrium. If it's the lowest energy state, no net reaction, then if a system is truly at equilibrium, the properties should be invariant over time because there's no net reaction, invariant over time. You can't prove equilibrium. You can only demonstrate the absence of equilibrium because at equilibrium there's no net reaction. So over time, no net reaction, properties invariant over time. And it could be attainable by multiple paths. So in other words, if I have ice as the equilibrium phase, I can make it by freezing water and get to the same ice at the given temperature and pressure, or I could sublime. But if I specify the pressure and the composition, I should always end up with the same system. So attainable by multiple paths. Attainable by multiple paths. Because it's a stable state, so it doesn't matter how you got there. It's a state function. And you know from your physics, a state function has the same value regardless of how you arrive there. And then the last thing is, I want to differentiate. See, these are all single phase, but some of them are just one element, some of them are just one compound, and some of them have a whole mix. And so we have a way of quantifying the degree of chemical complexity by using the term called component. The component. It's a measure of chemical complexity. Measure of chemical complexity. Measurement of chemical complexity. It's the number of chemically distinguishable constituents. Chemically distinguishable constituents. And again, these are definitions. I'll give you some examples so then the definition comes to life. Constituents. I like to think of it as the number of bottles you got to pull off the shelf to make the final product, okay? The building blocks. So for example, water is just water. You could say, but it's hydrogen and oxygen, but if you take 560 or some other thermo class, you'll learn that they're bound by mole ratio. You don't have freedom of hydrogen and oxygen, so it's just one bottle. Whereas to make white gold, you need three. You need three bottles. You need a bottle of gold, a bottle of silver, and a bottle of nickel. So that's a three-component system. And I'm going to designate the components by C with a circle around it, because C without a circle is already composition, concentration. Okay, so now we can put all of this together, and we'll show the difference between multi-component and multi-phase. So we'll make a little table here. Make a little table, and here I'm going to talk about one-phase systems and distinguish on the basis of components. So if it's single phase, single component, that's just water. One phase, one component, simple liquid. If it's two components, one phase, that could be calcium zirconia. I need a bottle of calcium and a bottle of zirconia in order to make this two-component single-phase system. And then to have 3 components, that's the white gold. White gold. It's still single-phase, but I need the gold, silver, and the nickel. Whereas if I come over here, I've got 2 phases. That could be slush. Slush, that's ice water. It's just one component. I just start with water and drop it down to 0 centigrade, and I'm going to end up with ice crystals in the water. So that's one component. I just needed one bottle, literally one bottle. All right, now what about 2 components, 2 phases? Well, we saw earlier when we started thinking about solubility, we did the bilayer with carbon tetrachloride and water. Remember we dropped potassium permanganate and iodine? And the potassium permanganate dissolved in the water and the iodine dissolved in the carbon tetrachloride. 2 different components. I need a bottle of carbon tet and a bottle of water, and they'll phase separate. They don't dissolve in one another because this is a nonpolar liquid and this is polar hydrogen bonded. That's the origin of phase separation. It's all about bonding, and bonding is all about electronic structure, and that sounds like a good topic for a class in chemistry. And then the last one here is obsidian. The snowflake obsidian, in which we've got the components are SiO2. So I'm going to have 3 components and end up with 2 phases. SiO2, there's some magnesia, and then the black comes from the magnetite, Fe3O4. So I've got 3 bottles off the shelf, and I end up with something that is crystalline and amorphous. So that's where I get the 2 phases. 3 components, 2 phases. It's great. It's great. So now I want to look at some stability maps, and we're going to start with the simplest of all, which is the one we know best from human experience, and that's water. So we're going to look at the one. So it's a 1 component. It's a 1 component. So for water, we start with C equals 1, and the example is going to be water. 1 component phase diagram. So we don't have a composition axis because the only thing we can vary is pressure and temperature. If we change composition, we've lost water. So it has to be axiomatically no variation in composition. All we have is the coordinates of temperature and pressure. Temperature and pressure. So there it is out of the book, and I'm going to draw it a little bit differently just to emphasize 3 of my favorite words, not to scale. Otherwise you can't see some of the subtle features. So overall it's a Y-shaped diagram. A Y-shaped diagram. And this is pressure. Let's make it pressure in atmospheres. If we make pressure in atmospheres, then our human experience is at 1 atmosphere. Human experience at 1 atmosphere. So at the highest temperatures, we expect to have vapor. Highest temperatures, we expect vapor, and at the lowest temperatures, we expect solid. Lowest temperatures, we expect solid, and in between, we expect liquid. And then if we look at the 1 atmosphere isobar, what's happening on this line? On the one side of the line, it's liquid, and the other side of the line, it's vapor. At this temperature, liquid and vapor coexist. I'd call that the boiling point, so I'm going to put 100 here. I'll call that 100. And we already learned from our little example of Mount Everest that this locus here, this line, is the liquid equals vapor 2-phase equilibrium. And you see how it changes? If I go to the top of Mount Everest, the pressure is less than 1 atmosphere, which means the boiling point of water is below the denaturing point. So this actually gives you the map. Or if I put the pressure cap on, I go up here. And you can use this in the kitchen again. If you love wild rice and you can't wait 45 minutes when you get home, use a pressure cooker. And what the pressure cooker does is it allows you to have liquid up to 130 degrees Celsius. You see, you can't steam it, you got to soak it in water. And you know the Arrhenius law. If you can get the temperature up by 30 degrees, you'll cut the cooking time in half. So how do you get water, liquid, at 130 degrees? And then you can cook quicker. Pressure, seal it, and then you got liquid water all the way, way up here. Now over here, this is solid goes to liquid. So this is the freezing point line. At 1 atmosphere, that's 0 Celsius. And you know, if you go skating, so let's say the ice is -5 Celsius, and you're here, but you put your weight on the blades, and the blades have small area, so force is, pressure is force per area. So that puts you up here, and now you cross, and now you glide on water, film of water. If you ever watch a hockey game, I grew up in Canada, we say, well, the ice is fast. Why is the ice fast? Because you get down to temperatures where you just get the right slickness of water. If the ice is slow, the temperature is so close that you get these big bruising hockey players, and they're moving up into here, and it's like they're dragging. And if you ever come from Minnesota or North Dakota, if you ever skated when the temperature gets down to about -20, -30, it's a different experience because you never get across this line. Your blades are just, they can't get a good grip. See, everything you need to know is here. Here's four-star chef. This is a prize-winning hockey player. We haven't even got off the 1 atmosphere line yet. Okay, so now I'm going to say this is single phase, right? It's just vapor. This is single phase, and this is single phase. It's all solid. And along this line, it's two-phase, isn't it? And along this line, it's two-phase. Solid liquid. This is ice cubes, isn't it? Anywhere along this line is ice cubes and water. Look at this one. This is liquid vapor. This is solid liquid. All three of them coexist here. All three of them coexist. This is P equals 3, which means ice cubes floating in boiling water. Ice cubes floating in boiling water. And this happens at only one point. It's called the triple point. This is the triple point, and its coordinates are, this is not to scale. So this is 0. This is 0.01 degrees C. It's a 1/100th of a degree higher, and the pressure here is 4.58 millimeters of mercury, which then you can convert using the 760 as 1 atmosphere. Oh, and this is solid vapor. You can go directly from solid to vapor down here. If you hang up your clothes on a line and it's -20 degrees outside, first thing that happens, the clothes freeze. You come back 5 hours later and the clothes are dry. Well, what happened? Did somebody take them in, run them around the clothes dryer and then hang them up for you? No, you're going directly from solid to vapor down in here. So here's the whole story of the phase diagram. But one last thing I want to point out. Here, you're at a given temperature and it's vapor. And then you squeeze, and now things get closer together, and you go from vapor to liquid at constant temperature. That makes sense, right? I start from vapor, constant temperature, I squeeze it, I get liquid, I keep squeezing, I should make solid. Here's vapor, I squeeze, I get solid, and I squeeze harder and I get liquid. That makes no sense at all. But that's what happens. What does this tell me? It tells me that the number of nearest neighbors in the solid is greater than the vapor. Yeah, I get that. But the number of nearest neighbors in the liquid must be greater than the number of nearest neighbors in the solid. This is an exception. When I see this negative slope, it means that ice cubes are going to float on water. That's what I learned from this negative slope. So let's put that down. dP by dt, when dP by dt is less than 0, this is for solid equals liquid, it means that the density of the solid is less than the density of the liquid. All from here. Okay, good. So let's look at a few other phase diagrams. So I think I've got a few things up here. Here's silicon. Here's silicon, pressure versus temperature. Its normal melting point is about 40. See, now I said normal melting point. See, after today's lecture, if somebody says, what's the boiling point of water? You don't go 100 degrees. You say, at what pressure? And they go, oh, I hate you. I hated you before. I'm going to use an adverb here. Now I really hate you. Okay, so this is the normal melting point of silicon. It's about 1,430 degrees centigrade, or 1,700 something Kelvin. And it also has this negative slope. And what does that tell you? That liquid silicon is denser than solid silicon, and it's a good thing it is, because we wouldn't have the microelectronics age if it weren't for that. We couldn't have Czochralski crystal growth and everything else that makes silicon dirt cheap. You know why it's dirt cheap? Because it's made from dirt. That's why it's dirt cheap. It's true. Here's aluminum. This is normal. This is the normal solid-liquid equilibrium. This is FCC metal, which is the closest packed. Axiomatically, the liquid must be less well packed. All right, so this is dog bites man, This is man bites dog. This is the unusual one. Okay, what else do we have here? Oh, nitrogen. Here's nitrogen. I drew this. So there's the 1 atmosphere line. Nitrogen boils at 77 Kelvin, and it freezes at about 63 Kelvin. And it's got the positive slope that you'd expect, and so solid nitrogen is denser than liquid nitrogen. And you can remember 77 Kelvin. You want to remember a few of these things. I wanted to point out to you that at atmospheric temperature, ambient temperature, you can remember 20/20 vision. So at 20 degrees C, it's roughly 20 millimeters of mercury is the vapor pressure of water. It's not exactly true, but it's close enough. I think it's really 24, but 20/20 is nice to know. And what's the street address for MIT? 77 Mass Ave. That's the boiling point of liquid nitrogen, 77 Kelvin. Okay? So I thought we'd do a few things here, and I'm going to show you a little bit of fun and games with liquid nitrogen. But first, I've been instructed I have to practice safe laboratory So I'm going to put on my lab coat. Yes. This is a nice lab coat. Mm-hmm. Yeah, look. You want to know. Oh, let's go back to this. They have to know where this is not just any old lab coat. This is a nice lab coat. This is from France. It's from Maison du Tech. You see, notice the collar. It's not that typical, Maison du Tech. Okay, let's go back to the phase diagram. All right, so Dave Broderick is going to help us here, so we're going to have some fun. I'm going to put on a face shield so I don't blind myself. All right, yeah. Here we go. All right, so let's get some liquid nitrogen. Sounds different, huh? Sounds terrible for me. All right, so we got some liquid nitrogen here, and I'll pour it into a dewar. So what happens when you wet a sheet of paper with ink with liquid nitrogen? What kind of bonding is there in liquid nitrogen? Look at, no running, because it's liquid nitrogen. I tell you, everything you learn here is so valuable and compared to all the other stuff you're learning. It's just, all right, so, okay, there's a couple of things. So let's look at glass transition temperature. So this is a latex glove. You can see it's above its glass transition temperature, and the cross lengths are snapping it back. What I'm going to do is take it down below its glass transition temperature and turn it glassy and brittle. So now it's below the TG. Okay. Here's some paraffin. Paraffin, which is also, there's a polymer here. Take the paper off. Okay, so here's paraffin. Look at the van der Waals bonds. Huh? This is van der Waals bonds. Now we're going to go below the TG. It's liquid nitrogen. It doesn't matter. Okay, you can hear it already. Huh? So it's now below the glass transition temperature. Well, what else have we got here? Oh, you've heard of the glass flowers at Harvard? Well, we've got glass flowers here. All right, so here's a rose. This is a rose. See, in the proteins, it's above the, it's soft. But now, we're going to put the, here we go. You ready? Oh, come on, it's not a kitten. What's the matter? It's still burbling here. We have to wait until it's dead. This is for science.
Okay, now it's below its glass transition temperature. Can you see this? Oh, I'm sorry, David, I should put this over on the other side. Okay. But maybe it's the red, or maybe it's because it's a rose. So here's a chrysanthemum. Let's see. Okay, today is your day. Here we go. Let's go. Get this thing moving. Yeah. So there you have it. There you have it. I think that's. Oh, and now there's one way. Maybe we go to the back to the slide. Let's show them what we're going to do next. Better put the gloves on for this. I'll have to write apology letters. Okay, so what we're going to do next is we're going to look at phase equilibrium. There's the melting points and boiling points of oxygen, argon, and nitrogen. And what you notice is that nitrogen boils at a lower temperature than oxygen and argon. So what I'm going to do is I'm going to pour some liquid nitrogen into this beaker, and then inside the graduated cylinder, I'm going to let it sit here, and we're going to condense air. And the result will be that we're going to start condensing liquid oxygen, and there'll be little bits of argon ice floating in liquid oxygen. And liquid oxygen is faintly blue, and it's paramagnetic, as you know, because it's got the unpaired electrons, which means that it will levitate in a magnetic field. I couldn't bring a big magnet in here, but we'll see if we can make some blue stuff. And it's foaming because this would be like pouring water into something that's, say, 300 degrees centigrade. But eventually the heat transfer gets low enough that you have stability here, and yeah. Okay. Oh, that's terrific. Okay, what else have we got? Oh, okay, so let's go back to this, Dave.
Slides, please, yeah. God, I hate this thing. It's all for science. Okay, what's next? Okay, so you've been looking at that nitrogen. Let's look what's next. Now if you solidify nitrogen, here you get a whole bunch of different polymorphs, different crystal structures. So there are about 5 or 6 different crystallographic forms of solid nitrogen. For that, we'd have to bring liquid helium, 4.2 Kelvin. Very cool stuff. Here's carbon dioxide. Now, it also has the positive slope, so solid will sink in liquid. But look at the interesting point here. The triple point is 5 atmospheres. At atmospheric pressure, you go directly from solid to gas. It sublimes. And that's advantageous. When we use carbon dioxide as a coolant, when it gives up its enthalpy to cool, it doesn't then turn into liquid. If you chill something with ice, with water ice, when it gives up its enthalpy, now you got the object is now swimming in water. And that's no good. So hence we have the term dry ice, because we go directly from solid to vapor. And we want to prove this. So what we've got here is a big block of dry ice. And so this is at minus 78 degrees Celsius, and it's still stable here. Well, it's subliming before your eyes. It's smaller than it was when we started the lecture. So what I'm going to do now, I guess I'm not wearing that stuff. Okay. I guess I better. They're going to write me up on some log. Say I'm teaching you bad practice, but anyways. All right, so what we're going to do is we're going to test the proposal that this actually goes. So I've got some water here. David, let's go now to the video. So we're going to take some water. I think we got water from France. It goes with the lab coat. This is Evian. Okay. Let me show. Evian. Okay. So I'm going to pour the Evian into the Florence flask. This is Florence. And pour the Evian into Florence. Florence is a round, and the Erlenmeyer is the flat one. This is Florence. So let's move this guy. You're going in the backstage for a while. You just keep condensing. All right. So now this is here. Now what we're going to do is we're going to put some
dry ice in there and see if we go directly from solid to vapor. I'll take a chip off the old block here. Okay, so now you can see that it's going directly from solid to vapor. So that's carbon dioxide bubbles, and we assume that the phase diagram is correct. I mean, another thing we could do is, I mean, I know what club soda tastes like. I could just test it, right? Yeah, it's carbon dioxide. Now, here's the other thing. You know, Schweppes likes to pride itself on tiny bubbles. They have a tagline, tiny bubbles, right? So here's Schweppes. And you can see Schweppes with their wimpy little tiny bubbles. Can you get that, Dave? But we have big bubbles. This is fantastic. I mean, this is pure. You can't get any better than that. I got Evian water and I got a block of carbon dioxide. I like making my own carbonated water. I've taken it to a new level. Okay. What else do we have? What else do we have? Well, let's see if we made any liquid oxygen here. Let's see. So, yeah. Want to try this? I don't know if we got anything in here. Oh, yeah. Oh, wow. Look. Okay, so that liquid in there, oh, I see, you've got separate things. I don't know if you can see it.
It's there.
It's condensing. It's condensing. That liquid in there, that's liquid oxygen. I won't drink this, though. But I can inhale it. It's pure oxygen. I could have a cigarette and just put the cigarette in there. What happens if I put the lit cigarette into the oxygen? All that happens is that it burns quickly, that's all. There's no explosion. It burns quickly. If you walk into a room full of oxygen, all that'll happen is you'll singe your nose, that's all. There's no explosion. It's just oxygen. There's no fuel. The fuel's just in the tobacco, and there's not much. It's not a problem. A room full of oxygen? Pfft. Okay, let's go back to the slides. What do we got here? Got some examples of other phase diagrams, I think. All right, so, yeah. Yeah. Actually, it's quite tasty. All right, so now here's zirconia. Now, here's the thing to know about zirconia. Look at all the different phases. And cubic zirconia is the one that has a high index of refraction, but it's stable only at temperatures exceeding 2,000 degrees C. So that's no good. So what I'm going to show you next day is that by changing the composition and adding calcium oxide, we open up this zone here that's labeled cubic, and we get it stable all the way down to room temperature. So it's an example of changing composition to get the stability of a phase that we want. This is carbon. So down here, the normal form, as we've learned earlier, the normal form is graphite. Diamond is formed at elevated temperatures and pressures, and this is liquid carbon. All right? Now, to make artificial diamonds, you could try putting graphite in an anvil and squeezing and squeezing and squeezing and coming up into here, and then it becomes metastable, and then maybe because the activation energy to jump from that sp3 hybridized state to sp2 is so high, the diamond is stable. So you don't have to go running home to see that if your diamond studs are now turning into graphite. They won't. Once you get into this zone, they'll stay. The activation energy is too high. You need more than 1/40th EV to do what is necessary. But in the 1950s, General Electric at Schenectady Research Labs reasoned that because carbon is so soluble in iron, they could dissolve carbon in liquid iron and then raise the pressure and temperature and then change to exsolve and cause carbon to precipitate out of molten iron. That's the birth of artificial diamonds. That's how they did it, using this concept but then dissolving it in molten iron.
Diamonds are a girl's best.
I don't know how that got in there. All right. Here's one for mercury. I looked it up using the tools that you've been taught here in 3091. So this is a paper phase diagram for mercury. And physicists drive me nuts because they plot temperature versus pressure. I want pressure versus temperature, so I just turned it around. And so here's the liquid line. So you know that liquid mercury is going to float on solid mercury, and there's a plurality of solid phases, and these are all different crystal structures. Now I've got a treat for you. I was in Barcelona several years ago, and I saw the Mercury Fountain that was made by Joan Miró in collaboration with Calder. Calder has the big sail outside of East Campus. So Calder collaborated with Miró back in the 30s and 40s, and this is in honor of the miners of Almaden, where there are cinnabar mines. And the miners fought bravely against the fascist forces of Franco, and Miró wanted to honor them. So here's their museum. It's a beautiful place up on the escarpment over Barcelona. And what I'm going to show you is a Mercury Fountain. This is liquid mercury. And the speed has not been altered. This is a liquid at room temperature, density 13.5, metallic bonds. Look at it. Very high surface tension. Look at the way it shimmers. Look at this shot. This has not been altered. That's the way it pours in a gravity field. It's really fantastic. And of course, mercury vapor is toxic, so the whole thing is in a, I cut that snippet out of the documentary. Okay, we don't want to see that. So they have the whole thing inside of a polymethyl methacrylate cage to keep the mercury vapor from affecting the people that work in the museum. Here's some phase diagrams from hell. This is bismuth. And look at bismuth. Bismuth is like water and like silicon, so the solid is less dense than the liquid. But look at all of these different phases. Here's sulfur. Sulfur's crazy. Look at phases in the solid phase. There's even phases in the liquid. Different phases. There are allotropes. Here's sulfur, elemental sulfur, the disulfide, hexasulfide. It makes rings. It makes long chains. And these are called allotropes. They're different forms of the same element. So oxygen is O. There's the atomic molecule and the triatomic molecule, which is ozone. These are all allotropes of oxygen. What else do we have here? Okay, this is polymorphs. So this is alpha goes to beta. See, different crystal structures. You can see with your naked eye what's going on here. Different crystal structures. And then this goes to lambda, and then finally they're pouring here. And if you get a very high cooling rate and you got those long chains, what happens? You don't form the crystal, you form the amorphous form. So they'll call this forming plastic sulfur. We know better. It's amorphous sulfur. It's not plastic sulfur. Here's water complete diagram. Now this is in kilobars. So there's all the different phases of water. There's the negative line. That's this thing here, but at very, very high. Look at all the different phases of water, and they have numbers on them. If you read Kurt Vonnegut, Cat's Cradle, there's ice 9. If you get that going, it freezes the whole world, right? But here's, I draw your attention to this one. You see this point here? This is ice 7. At 100 degrees C, it's solid. You need 25 kilobars. So we can go over to the lab, take some water, put 25 kilobars on it, make solid ice at 100 degrees C, and it'll be stable. Look, this is minus 78, and it's been here for a long time. So now I come into a cocktail party with this. I drop this ice cube into a glass of aqueous beverage. It sinks to the bottom, and the beverage heats up to the boiling point. That's what this is telling you. That will get you popularity instantly. How did you do that? How did you do that? And up here is the supercritical fluid, the last thing we haven't said anything about. Look at, if you take a gas and you keep squeezing it, eventually the gas molecules are close enough together that they're indistinguishable from the liquid phase. Or if you start here with the liquid and you keep raising the temperature, the density goes lower and lower until the molecules are far enough apart that you can't tell this zone whether it's a rarefied liquid or a highly compressed gas. The properties crisscross. This is supercritical. It has liquid-like transport properties and vapor-like chemical properties, so you can end up doing things that are very, very different. I'm going to give you an example of decaffeinating coffee by taking the coffee, going up into the supercritical regime, which allows you to extract the caffeine and not brew the coffee. See, you want to just get the one. You don't. Otherwise, if you just heat it up, you'll make the coffee. So here's an example. It's called solvent extraction. Historically, the solvent was methylene chloride, which is also used as paint stripper. We don't do that anymore to coffee. They did in the 60s. They did. They also used trichloroethylene. It works really well to leach out the caffeine. How much is left in there for you to taste with your coffee? I don't know. Maybe that's why people were so excited in the 60s to drink their decaffeinated Sanka. I don't know. But anyway, so you take the green beans in carbon dioxide as supercritical and drop the caffeine level, and then you play with temperature and pressure to go over the KSP. The caffeine salts out, and then you recycle the CO2. Okay, I hope I've given you some introduction to phase diagrams, and we'll see you on Monday.